So we think of heat transfer. This is a very simple topic, and definitely one question will be asked in any one of the competitive exams. So generally, heat transfer is divided into three types. So one is conduction, and the second one is convection, and the third one is radiation. The third one is radiation. So for the process of convection, so for the process of conduction, so definitely a medium is required. A medium is required definitely. For the process of convection, for this also medium is required. Medium is required. And for radiation, medium is not required. Medium is not required actually. So in the case of conduction, here actual displacement of molecule takes place. In the case of convection, in the case of conduction, without the actual displacement of molecule, heat transfer will take place. In the place of convection, actual displacement of molecules exists. And the radiation, the matter is not required. Generally, the heat will be transferred in the form of radiation. So we will discuss one after the other. So first we think of conduction. First we will discuss heat conduction. First we will think of heat conduction. So heat conduction means, so this is a kind of heat transfer without the actual displacement, without the actual displacement of molecules, without the actual displacement of molecules, without the actual displacement of molecules, heat transfer will take place. Heat transfer will take place from one end to the other end, one end to the other end of the given body. So this is known as heat conduction. So to understand this heat conduction, so we are thinking of a solid. Suppose this is a solid body. So we are taking number of molecules here. So we are having A, B, C, and D, E, and F. We are having number of molecules. So whenever you are providing heat energy to one end, after absorbing the heat energy, the A uses to oscillate, and after shifting the energy to the neighborhood molecule, that is B, again the molecule will bring back to oscillation. So that means until it has energy, until it possesses energy, it makes oscillation. But after shifting the energy to the B molecule, again the molecule A brought to its original position. And after absorbing the energy by the B from A, again it undergoes vibration or a kind of oscillation, and it will shift the energy to the neighborhood C, and it will come back to its original position. So the same story continues. So until the shifting of heat energy takes place to the neighborhood molecule, so the molecules undergo some kind of vibration. Some kind of vibration. After shifting the energy, again the molecules will bring back to its original position. So that means here we need to understand that the molecules, so the molecules undergoing so non-harmonic oscillation or unharmonic oscillations, non-harmonic oscillations, they are undergoing non-harmonic oscillations, and there is no displacement of the particle because after some time the molecule will bring back to its original position. So this is a kind of process heat transfer is known as heat conduction. From the diagram, it is very clear that So the conduction is more in solids because in the case of solids, the molecules are closely packed. So therefore, the interaction will be maximum. The interaction will be maximum between adjacent molecules. So therefore, simply we are taking conduction is more in solids. Conduction is more in solids. So slowly we are taking the ABCDs of conduction. So we are taking the heat conduction through a rod. So we are taking the heading as heat current through a rod. For example, so I'm taking a rod of area of cross section A, and let us say its length is D. Let us say its length is D. So one end is maintained at a higher temperature theta1 and the other end is maintained at a lower temperature theta2. So we are saying that theta1 is the hot and theta2 is the cold one. Theta1 is hot and theta2 is the cold. So according to our practical observation, so the amount of heat energy exchange between A and B, Q is proportional to area. So that means if the area of cross section is more, automatically the rod will transfer more amount of heat energy. Suppose if the area of cross section is more, so the more amount of heat energy will passes to the rod. Similarly, Q is proportional to delta theta. If the temperature difference is high, then more amount of heat energy will be processed, and heat energy is inversely proportional to length. So if the length is more, so obviously as the length is more, it will loses more amount of heat energy during its transfer. Suppose if length is less, so more amount of heat will be transferred to the area of cross section. So by combining all these things, so we are going to get the following expression. And one more thing is the amount of heat energy transferred is directly proportional to time. So if the time of transfer is more, so definitely if time of observation is more, then more amount of heat energy will be transferred to the rod. So after combining all these things, we are going to get A into delta theta into d by d. So we are removing the proportionality and placing a constant. So Q is proportionality equivalent to K into delta theta into T by T. So that is Q by T equivalent to K into delta theta by T. Q by T equivalent to K by K into delta theta by T. So we will call the Q by T as heat current. We are calling H equivalent to Q by T, H equivalent to Q by T, and H is called as heat current. So that equivalent to, we have an expression K into delta theta by T. So this is very important and this is the backbone of the topic conduction. The only formula we are having, this is very, very important. So now we will analyze each and every one. So here K means, so this is coefficient of thermal conductivity. Capital A means area of cross section. So area of cross section we need to take, generally we are having circular rods. So for circular rods we will take pi r square. Circular rods where r is the radius. Of cross section. And that equivalent to capital A is equivalent to A square. So this is for square rods. Where A is the side length. So A is the side length. Suppose if you have rectangular rod, they will take length into breadth. But most of the cases is either circular or square one. So this is delta theta. Delta theta is temperature difference. Delta theta is temperature difference. Or it can be called as the theta hot minus theta cold. Theta hot minus theta cold. And we are taking D means length of the rod. D means length of the rod. So we are taking. So here we are converting that heat current formula into a specific format. So we will write H is equivalent to instead of writing Ka into delta theta by D, just I am writing in the form of delta theta by D by Ka. And H is equivalent to delta theta by, and instead of R by Ka, I am taking this as the thermal resistance. So I am taking this is the thermal resistance. So this is very important formula. H is equivalent to delta theta by R thermal. So that means actually R thermal equivalent to, we will take it as D by Ka. Now the question is, how do you get the form and why we are calling the D by Ka is as the thermal resistance? We know in electrostatics, I equivalent to V by R. So we are thinking of electrostatics. Or current electricity, whatever it may be. The current terms we are discussing. So we will use both of them, current electricity and electrostatics. So when we use I equivalent to V by R, so we will say that when we think of a conductor, we have the current flow. When there is potential difference. So V equivalent to VA minus VB I am taking. When it is not equal to 0, so then only the electric current will exist. So similarly, you can see that in the case of a rod, for example, I am taking the case of a rod. So let us say this is the theta 1 and this is the theta 2. So whenever we are having temperature difference, so that is whenever the delta theta is not equal to 0, whenever we are having temperature difference between the ends, so then only we have the passage of heat per unit time will exist. So that is heat current will exist. So that's why simply we are comparing that this heat current H is comparable to electric current, and this electrical resistance is comparable to thermal resistance. Electrical resistance is comparable to thermal resistance. So we can remember it very beautifully. So because in the electrostatics we have a shortcut actually, or we have a consideration. So I'm taking here. So here in suppose we think of current electricity. So where we are having a resistance equal to rho L by A. Rho is the resistivity, or we are having 1 by 1 by sigma into L by A. So where we used to call sigma is nothing but conductivity. Simply just by comparing these two, we are going to remember the thermal resistance always. There is no need to by heart or memorize. So similarly, I am writing thermal resistance. So instead of length, I am taking length D, and instead of conductivity, I am taking here the heat conductivity, and area of cross section is same. Here. For which case we will use which formula? First, now we will discuss. Suppose we have a rod. Is given. This is the theta 1 and this is the theta 2 are given. Area of cross section is A and the length is D is given. D is given. So for the numerics, so this is very important. For the numerics, if you are interested to find out the heat transfer, if you are interested to find out the heat transfer, just we will write Q by T is equivalent to Ka into delta theta by T. We know about every parameter. Q by T equivalent to Ka delta theta by T. For a while, we will analyze the problem. For a while, we will analyze the discussion actually. For example, we are having one end. So we are having one end. We are having one end. For example, so we are having left side. We have a hot chamber of water. So maybe at 100 degrees centigrade, and the right side we are having some ice cubic box, ice cubes. So slowly we will analyze every term. So in this case, so whenever the amount of heat shifted from hot end to the cold end is used to melt the ice. So whenever that case, we will use ml. So therefore, simply we will write ml by T is equivalent to Ka into delta theta by D, or m by T is equivalent to, we will write Ka into delta theta by T into capital L. So here we need L means latent heat, capital N means latent heat of fusion of ice. So that is already we know this in the CGS system 80 calorie per gram we used to say. Or if you are interested in SI, we will write 80 calorie per gram is nothing but 4200 joule per kilogram we are taking. So this M by T is called as rate of melting of ice. This M by T is known as rate of melting of ice. So that we need to remember. This is rate of melting of ice. Rate of melting of ice. So next, after taking this, so we know everything. K is the quotient of thermal conductivity, and A is the area of cross section. Delta theta is the temperature difference. D is the length, and capital L is latency. And when we think of K, so that is quotient of thermal conductivity, you need to remember that it is constant for a given material or for a given rod. Like the density, so we know that like density and Young's modulus. So, as long as you take the same material, the density of a material is constant, or the Young's modulus of the material is constant, or coefficient of thermal conductivity of a material is constant. So we will assume like this. So generally, we will use this Q by T equivalent to Ka delta theta by D approach for numerics. So you need to be very careful. So whenever we are having integration related models, so in such a case, we will use dq by dt. Instead of q by t, we are writing dq by dt equivalent to dt. This is time minus k into dt by dx. So this is the form. So this is the form we are going to take. So this is the form we will take when there is a need, of depending on the situation, differentiation or integration. So differentiation and integration models, for these models, so we will use this formula dq by dt equivalent to minus k into dt by dx. So generally, this is the situation we need. Suppose I am taking an example, so then you will get a clarity. For example, we are having two circular or two hollow spheres. We are taking two hollow spheres. So between the hollow spheres, we are filling with some material. Between the hollow spheres, we are filling with some conducting materials. So this is of radius r1 and this is of radius r2. So we are taking the temperature difference. We are taking the temperature difference as theta 1 and theta 2. So let us say theta 1 is greater than theta 2. Theta 1 is greater than theta 2. Now they will ask for the rate of conduction H is proportional to in terms of R1 and R2. So they will ask. So we will take dq by dt. Here variable, taking of variable is very, very important. dq by dt equivalent to minus k into. So here area changes whenever you observe. So whenever you move away from here to here, the area changes. Area is the variable here. So minus k into 4 pi r square into dt by the dx means dr. Dx means dr. So this is a heat current. It is a constant. It is a constant value. H is equivalent to minus k into, or we are taking for small radius if we take for this area. I'm taking this as dh. dh equivalent to minus k into 4 pi r square by dt by dr. Or we will consider that dr into r power minus r. dr into r power minus 2 is equal to minus 4 pi k into dt 4 pi k into dt by dh. So actually we need h. So integral 1 by r power minus 2 into dr equivalent to minus 4 pi k. This dt is a constant, so there is no need of worrying about this. This is theta 2 minus theta 1 by dh. So we will apply integration. So after solving this, we will get h is proportional to r1 r2 by r1 minus r2. So just by taking integral of x power n plus 1 by n plus 1, we are going to get that formula. So for the case of integration and differentiation, we will take dq by dt equal to minus k into dt by dx. And one more thing we need to focus. So if you take the square cube, or if you take cube, if you take cube of side length a, అంటే జనరల్గా ఇక్కడ ఉండేటువంటి కన్ఫ్యూజన్ ఏంటి అంటే స్టూడెంట్స్కి, ఫర్ ఎగ్జాంపుల్ వన్ సైడ్ వీఆర్ హ్యావింగ్ హాట్ జంక్షన్ అండ్ వన్ సైడ్ వీఆర్ హ్యావింగ్ కోల్డ్ జంక్షన్. సో ఇప్పుడు మనం ఎట్లా తీసుకోవచ్చు చెప్పు. ఏ అంటే సపోజ్ సైడ్ లెంగ్త్ ఈస్ ఏ, సపోజ్ ఐఎమ్ టేకింగ్, వెదర్ వీ నీడ్ టు టేక్ 6a square or a square. సపోజ్ అదే నాకు కావాల్సింది, అది తప్పు నన్ను 6a square కాదు, ఎందుకనేది ఒకసారి చూడు. q by t equivalent to k delta theta by d. Actually this is the hot end and this is the cold end. So the heat transfer will take place in this way. So whenever the heat transfer will take place, only one phase, I mean only one sides are helpful. So that is cumulatively what we will call it as only this area is helpful. This area is helpful. So that's why here capital A should be taken as a square, where A is side length. Where A is side length.
Okay, sir.
So next, we used to discuss about when the rods are connected in series. When the rods are connected in series. When the rods are connected in series. For example, I'm taking two rods. So this is one rod and this is another rod. So almost So the students will often confuse that for series, area cross section should be remained as constant. But అలా ఉండాలని ఏం లేదు. కొన్ని ప్రాబ్లమ్స్ లో ఉండొచ్చు, కొన్ని ప్రాబ్లమ్స్ లో ఉండకపోవచ్చు. But in most of the cases, area cross section is constant. First, simply or beautifully we will remember series. In series means I constant. So actually, when I'm speaking about the current electricity or electricity terms, current electricity. So in the current electricity, suppose if we have two resistors R1 and R2, two resistors R1 and R2. So when two resistors R1 and R2, they are connected in series means the people will often confuse whether I remains constant or V remains constant. Just the simple trick is in the series name itself we have I. So therefore I is constant. So by comparing with electricity, here I is comparable to H. So therefore H is equivalent to constant. H is equivalent to constant. When the two rods are connected in series, H is equivalent to constant. And here we can see whenever there is potential difference between V1 and V2, so then only we have flow of current. So we have flow of current. Similarly, whenever we have temperature difference between the ends, LHS and RH, so we have the flow of heat energy. We have the flow of heat energy. So we have the flow of heat energy whenever theta1 is not equal to 0, whenever we are having temperature difference. So the first important point is H is constant. So when H is constant, we will analyze slowly K into delta theta by D equivalent to constant. K into delta theta by D equivalent to constant. Suppose I'm taking area of cross section is same, and this is made up of K1 rod, and this is made up of another material K2. And let us say this is the junction, and junction temperature is theta. And if we take this is the length of D1 and this is the length of D2. First, we will focus on analyzing the question or given scenario. So whenever the two rods are connected in series means you need to write like this: H is equivalent to constant. K delta theta by D equivalent to constant. So from here we are having two possibilities. In one case, the two rods made up of different material. In another case, the two rods made up of same material. Suppose I'm taking the two rods made up of different materials. So we will take that is K1 into area means this is theta1 minus theta by D1. So that equivalent to K2 into A into theta minus theta2, K2 into A into theta minus theta2 by D2. So therefore, so we will take K1A1, K1A theta1. So K1A theta1 or area cancel. We get K1 D2 into theta1 minus theta2 theta, that equal to K2 D1 into theta minus theta.
Sir?
So simply by solving this, we will get we will solve no issues. K1 D2 theta1 minus K1 D2 theta, that equivalent to K2 D1 theta minus K2 theta2 D1. So by taking this K1 theta1 D2, this minus becomes plus K2 theta2 D1 equivalent to theta into K1 D2 plus K2 D1. Just by taking this, we will get K1 theta1 D2 plus K2 theta 2 D1 by K1 D2 plus K2 D1. So there is no need to memorize this formula. Just only you need to understand this. You need to understand this. So that's all. So next, we will think of same length. For example, if D1 is equivalent to D2, if D1 equivalent to D2, so we will take the junction temperature theta equivalent to K1 theta 1 plus K2 theta 2 by K1 plus K2. K1 plus K2. In this way, we used to find out the junction temperature if D1 equivalent to D2. Again, I am stressing there is no need to memorize this formula. Only you need to understand that is H is constant. Only H is constant. That is K into delta theta by D equivalent to constant. And also, we will see the next point in series. So suppose I am taking when two rods are given. So one is of K2 and the another is of K1. So now they will ask for find effective coefficient of thermal conductivity. So then we will say this is having a resistance R1 and this is having a resistance R2. So let us say it is having a length D1 and it is having a length D2. So then as the two are in series, just we will write the series resistance R is equal to R1 plus R2. Because the fluid resistance is comparable to series resistance in electrostatics or in electricity terms. So R is equivalent to R1 plus R2 we are writing. So this is very similar to electricity we are doing. So R1 means suppose we are taking D1 by K1A plus D2 by K2A. And this RS means, so this is the system related, total system. So we are taking the total system length as D1 plus D2 and K series and area cross section. Total system means, so you're calling as the rod as single rod. This is a single rod of coefficient of thermal conductivity K and having a length of D1 plus D2 and having a resistance, let us say R. So by solving this, we are going to get Ks is equivalent to D1 plus D2 into K1 K2 by K1 D2 plus K2 D1. So this is very famous. If D1 equivalent to D2, we are going to have Ks is equivalent to 2K1 K2 by K1 plus K. So this is the another formula we need to remember. So this you have to remember. Ks is equivalent to 2K1 K2 by K1 plus K. And so one more analysis over this series combination is, so H equivalent to, also we will take in this format delta theta by R. When H is constant, automatically delta theta is proportional to R. So delta theta is proportional to R. So we use that analysis. H is proportional to delta theta by R. So our intention is to find out junction temperature in the given diagram. The given figure, we need to find out the junction temperature. So simply we will understand that. So here, so this is the current, this is the heat current. So because this is the hot end, and these are relatively cold ends. So we can see that the amount of heat current passing through here may be split into these two branches as H1 and H2. H1 and H2. So simply by analyzing that, we are going to do the problem. So first, before analyzing, first we need to analyze the question. So when we are taking heat current means H equivalent to delta theta by resistance means D by Ka we are taking. So here the problem is given that they are having same length. They are having same length. Suppose they are having D. So first we are analyzing H equal to delta theta by D by A. So D is same and as well as A is also same. So H is equivalent to we have K into delta theta. K into delta theta. Now I am taking H is equivalent to H1 plus H2. H1 plus H2. So we know that as this is 100, the temperature difference for first rod is 100 minus theta. For the temperature difference for the 2K rod is theta minus 40. For the temperature difference for the 4K rod is theta minus 10. Because the theta is the junction temperature. Always the junction temperature lie between hot and so it always lies between hot and cold values. Suppose if you are taking this is the theta hot and the theta cold. So this is the relation. It always lies between theta hot and theta cold. H means I am writing K into delta theta means for the first rod we are writing 100 minus theta. 100 minus theta. H1 means that is equivalent to 2K into theta minus 40 plus 4K into we will write theta minus 10. So theta minus 10. So we are cancelling K. So we get 100 minus theta equivalent to 2 theta minus 8 plus 4 theta minus 40. We are going to see. So we have 100 minus 80 minus 40 means minus 120. So therefore, so that is equivalent to 220. 6 theta plus theta means 7 theta. So therefore, theta equivalent to 220 by 7 degrees centigrade. So in this way, we can find out the junction temperature for a given situation. In this way, we'll find out. So we will focus on the basic parameter, temperature gradient. So in the physics, whenever you are having a term gradient, in the denominator, you are going to have length. Suppose if somebody asks for temperature gradient, so they will write delta theta, temperature difference by length. So that is the temperature gradient. So this is temperature gradient. For example, so I'm taking this is theta 1 hot end and theta 2 cold end, and this length is the. So therefore the temperature difference is theta 1 minus theta 2 by. Okay. Next, the most important thing is steady state. So in the questions, often they will come across this term. A rod is in steady state condition. So first we need to analyze what do you mean by steady state. So the people will confuse that in steady state, the temperature is constant. For example, this is theta 1, this is theta 2. So in steady state means we need to analyze that the H remains as constant, not temperature difference. H remains as constant. So H remains as constant means now we will analyze H equivalent to K into delta theta by D equivalent to constant. For single rod you are taking, so therefore K is equivalent to constant and area of cross section is automatically constant. So we will see that delta theta is proportional to D. So that means for same lengths, suppose if we make the rod into many partitions of same length, if we make the rod into many partitions of same length, for equal lengths, we have equal temperature differences. For example, for 1 centimeter, if we have 10 degrees centigrade loss, for next 10, for next 1 centimeter also, we are going to have 10 degrees centigrade loss. Suppose I'm taking an example. This is 100. For every centimeter, we lose 90, 10 degrees centigrade. So therefore, we get 90 here, and 80, and 70, and 60, and so on. We are going to get. So that is the importance of study. For example, I'm taking a rod. This is a rod. This is a rod maintained at temperature difference 100 degrees centigrade, and the other end is at 0 degrees centigrade. Now we are taking another rod. Now we are taking another rod. So this is at 25 degrees centigrade, and we need to find out the junction temperature. And the total length is given as 1 meter, let us say. The total length of the rod is given as 1 meter. At certain distance from heart end, you are keeping a rod. This is a rod. This is a rod. You are keeping the position of the rod such that there is no heat flow. There is no heat flow. There is no heat flow in the vertical rod. In the vertical rod in steady state. In the vertical rod in the steady state. There is no heat flow. So there is no heat flow through the vertical rod in steady state. Suppose this length is x we are taking. We need to find out the position. We need to find out the position of the rod where we need to keep the vertical rod with respect to the horizontal rod. When this is 1 meter and this is x, and automatically this length is 1 minus 1 minus x. So the question is clearly given steady state. So the total system is a steady state. So whenever this is the discussion, this end of the rod is maintained at a temperature 25 degrees centigrade. So simply we will think that this is the part A and this is part B. And we will write H is equivalent to Ka into delta theta by D. H is constant. You are taking the same material, so therefore A is constant. You are taking area of cross section also same, A is constant, because only we are taking for horizontal rod. So therefore delta theta is proportional to B. So we are writing delta theta A for A segment, and B segment we are writing that equivalent to dA by dB. So delta theta A means that is delta theta A means higher minus lower, 100 minus 25 we are taking by theta. Delta theta B means 25 minus 0. So that equivalent to dA by dB we are taking. So dA means x, and this is 1 minus x. 100 minus 25 means 75. 75 by 25 equivalent to x by 1 minus x. So by taking this, we will get 3 minus 3x is equivalent to x, or 3 equivalent to 4x, or x is equivalent to 3 by 4 meter. So such that 0.75 meters. So what is the conclusion is, you need to place the vertical rod at a position of 3 by 4 meter from the heart end, such that the horizontal rod, the total system is in steady state. So another important phenomena on this is growth of ice, growth of ice over a pond. So we have a pond in cold countries. In winter season, there may be some layers of ice. Layers of ice. So here the question is given that what is the time taken to increase the thickness of ice layer from x1 to x2? From x1 to x2. So this is also possible by means of conduction. So whenever the heat is given to this, the heat is passed through the layers of water. Because of that heat exchange, the layers of the ice will be frozen. So we have a condition, the time difference or time interval that will be equal to rho L by 2k theta into x2 square minus x1 square. So this is delta t means time interval, and L means latent heat of ice, and K is coefficient of thermal conductivity, and theta is so this is the temperature. Theta is the temperature of atmosphere. So technically it is minus theta. So this is minus theta. X1 is initial thickness of ice, and X2 is final thickness of ice. So this is very, very important. So, and the rho means density of ice, that is fixed 0.9 gram per cc, 0.9 gram per convection. So convection means that this is a kind of heat transfer with the actual displacement of molecules. And this convection is divided into two types. One is natural convection, and the other is forced convection. So let us take any breeze, land breeze, sea breeze, or trade breeze. So we will take any breeze as the example of natural convection. So I'm taking another example. The hot air in our room may be escaped through the ventilator, from the room through the ventilator. So that is natural convection. Nobody is forcing it. So the forced convection means, suppose if you take exhaust fan or AC, so we will force the heat to move from one place to another place by means of air we are taking. So that is the difference between natural convection and forced convection. So here you need to remember that natural convection is possible whenever the gravity is not equal to 0. Because whenever the hot air escapes from the room, so the hot air is less denser. So because of variation in density, it will feel lighter. So it will escape from the room through the ventilator. So when there is G is not equal to 0, when there is G equivalent to 0, suppose if G is equivalent to 0, gravity free region, there is no heavier particle and no lighter particles. Everything will float. So therefore, in gravity free region, we need to understand that in gravity free region, only forced convection is possible. Natural convection is not possible. only forced convection is possible. So that is the main difference. So this is G is not equal to 0 when that means in gravity is present. Gravity is present. This is possible. This convection is possible. This convection possible. So already we know about the forced convection. So here no need of G, no need of gravity, no need of gravity. And one more thing is one more phenomena of natural convection is it can happen in only in vertical direction. Only in vertical direction. But the forced convection, it can happen in any direction. It can happen in any direction. So we have only one formula here. So dq by dt is equivalent to h into a into delta theta. For example, we have a human body. Suppose the question will be given like this. He has a black scar. His chest has a black scar of area of cross section A. And his temperature of the body is theta and the surroundings temperature is theta naught. So then they will ask her what is the rate of heat transfer from his black scar. ఇలా అడుగుతా ఉంటారు. అప్పుడు మనం ఏం రాస్తాం అంటే హెచ్ ఈజ్ నథింగ్ బట్ కన్వెక్షన్ కాన్స్టెంట్. దే విల్ ప్రొవైడ్ convection constant. Capital A means here surface area. Surface area. Delta theta is nothing but it is the temperature difference between body and surroundings. Temperature difference between the body and as well as surroundings will be there. Heat radiation. So this is a kind of heat transfer without even the need of medium. Without any help of medium, the heat transfer will take place. So first here we will take the Stephen's law. The Stephen's law, that is rate of heat transfer. We used to call this as RH, rate of heat transfer, or Q by T. You take Q by T equivalent to we used to take sigma AE T power 4. Sigma AE T power 4. So or we will call, so this is the rate of heat transfer. Rate of heat transfer, or we used to call it as power. The power dissipated. Power dissipated. And sigma is Stephen's constant. So that equivalent to 5.672 into 10 power minus 8 watt per meter square Kelvin power 4. E means emissivity. E means emissivity. So in the question, if it is specified, we need to take that value. Otherwise, we will take emissivity as 1 by treating this as the given body as black body. మన క్వశ్చన్లో ఎంసిటివిటీ వాల్యూ ఇస్తే మనం తీసుకుంటాం, లేదంటే మనము ఈ అనేటువంటి 1గా తీసుకుంటాం. సో క్యాపిటల్ T ఈజ్ ది అబ్సల్యూట్ టెంపరేచర్ ఆఫ్ బాడీ. Absolute temperature of the body. Next, we are thinking of Stephen-Boltzmann law. Stephen-Boltzmann law. So this is practically valid. So actually, while we are studying Stephen law, we never thought of the surroundings temperature and surroundings interaction. But here we will consider the surroundings interaction also. Suppose I am taking, this is a body, this is capital T and this is T naught. So the heat transfer or the heat exchange the heat lost by the hot body to the surroundings is Q by T equivalent to sigma A into T power 4 minus T naught power 4. T naught power 4. So here the new one is T naught. T naught is nothing but this is the temperature of surroundings. This is the temperature of surroundings. So the remaining values are same. So you need to think of that. This is the Stephen's law and as well as Stephen's Boltzmann law. So after taking Stephen's law and Stephen's Boltzmann law, now we used to discuss rate of cooling. This is very important for means. So rate of cooling or rate of fall of temperature, or it is called as rate of fall of temperature. Fall of temperature. So according to the discussion, we are taking dq by dt equivalent to minus Ka into, or we will take it dq by dt equivalent to sigma A into T power 4 minus T naught power 4. We are taking T as the T naught plus delta T, and this delta T is very small. We are taking very small temperature difference. So by substituting here sigma A into T naught plus delta T whole power 4 minus T naught power 4. T naught power 4. By solving this, so we are going to get ms into d theta by dt. That d theta by dt you are calling as rate of fall of temperature equivalent to, by solving this we will get minus sigma A by ms into 4 into delta t by taking binomial approximation. We won't need all these things. So here finally what we are taking is d theta by dt is proportional to the temperature difference. This is theta minus theta naught. But you need to understand that theta is the temperature of the body and theta naught is the temperature of surroundings. For example, if the temperature of the body decreases from theta 1 to theta 2 in a given time t, so simply we will write theta 1 minus theta 2 by, I'm taking the time interval as t, t is proportional to, this is the main temperature of the body minus surroundings we are taking. Or theta 1 minus theta 2 by t is proportional to theta 1 plus theta 2 by 2 minus theta naught. So this is one of the important principle we need. This is the one of the important principle we need. And suppose if you are thinking of theories, so this is also very important. Rate of fall of temperature. So that is also very important. And you need to understand that. So this is possible whenever we are taking delta t by delta t is very small. So that is this kind of, or the above approximations are possible. The above approximations are possible when delta t is not when delta t less than 35 degrees. Less than 35 degrees. So for small temperature variations only, delta T or delta theta. So we know that temperature difference in centigrades or kelvins both are same, is less than 35 degrees. So then only we used to take this kind of approximation. And another drawback of this Newton law of cooling, this is called as Newton law of cooling. Newton law of cooling is, so the body surface, it should emit the heat energy at uniform rate from entire surface. This is also practically not possible. This is also practically not possible. So simply just we will remember this equation. We will remember this equation. This RF is proportional to A by M. So this is very, very important. So we are having some theory analysis for the rate of fall of temperature and the rate of heat transfer. ఇక్కడ వీటిని థియరీ క్వశ్చన్స్ ఎలా వస్తాయి అనేది మనం చూద్దాం. ఫర్ ఎగ్జాంపుల్, సో హియర్ ఐఎమ్ రైటింగ్ రేట్ ఆఫ్ లాస్ ఆఫ్ హీట్ అంటే ఏంటి, రేట్ ఆఫ్ ఫాల్ ఆఫ్ టెంపరేచర్ అంటే ఏంటి మనం చూద్దాం. రేట్ ఆఫ్ లాస్ ఆఫ్ హీట్ అంటే we used to take dq by dt, so that equivalent to sigma ae into t power 4 minus t naught power 4. So finally, in terms of dimensions, RH is proportional to area. So similarly, when we think of rate of fall of temperature, rate of fall of temperature, rate of fall of temperature. So that is RF. Just now we have taken it is proportional to A by M. Suppose when we think of spherical bodies, we will take area means 4 pi r square, mass means volume into density 4 pi by 3 into r cube into rho into s. S is also there in next question. So rate of fall of temperature is proportional to 1 by r rho s. This is very, very important. So rate of heat is proportional to the area proportional to r square we are taking. So by thinking of these two considerations, we are going to understand some given questions. For example, we are having one application. We have two solid spheres. We have two solid spheres of same material. So whenever they are made up of same material, the density is constant and specific heat is constant. Density is constant, specific heat is constant. And have same surface area. If it is, the question is given like this. So then discuss the nature of rate of heating and discuss the nature of rate of cooling. So therefore, we will say that RH is proportional to area only. So RH is proportional to R square. That is a constant. But when we are discussing about this rate of fall of temperature, RF is proportional to A by M. So that is nothing but 1 by R. Same material, same surface area means both are same. RH remains as constant and RF also remains as constant. If they have different area, in the same discussion we are taking, if they have different area, different radius, so only rho constant and s constant, so then we will say RH is proportional to R square. So therefore R1 by R2 is equivalent to small r1 by small r2 whole square. And also here rate of fall of temperature I am taking, RF is proportional to 1 by R. So that is R1 by R2 equivalent to small r2 by small r1. ఇలా మనం తీసుకుంటాం. Next, we are taking the second one. We are taking the second situation. Suppose if two solid spheres or we will take like this. Two spheres, one is hollow, and the other is solid, So then discuss the situation. Discuss the situation. So when they have same area, suppose if it is given that we have same area, it is given the same area. So we know that RH is proportional to A and A is fixed. So therefore, rate of heat loss for hollow, it should be equivalent to RH for solid. ఇలా మనం తీసుకోవచ్చు. Next, if you are taking rate of fall of temperature, RF is proportional to 1 by R rho S, or we will take A by M. In the present case, area of cross section is area of surface is same. So therefore, rate of fall of temperature only depends upon mass. So we know that for hollow sphere, the mass is less. So therefore, rate of fall of temperature for hollow is more than rate of fall of temperature for solid. So we are taking this kind of approach. But the last application of Newton law of cooling is whenever the temperature difference between the body and surroundings, delta T or delta theta, is more than 35 degrees centigrade. So in such a case, how we will take? Now I'm taking the discussion. Suppose a body of temperature theta 1 kept in a surroundings theta naught, and cooled to a temperature theta. So we are thinking of Newton law of cooling special cases. Newton law of cooling special discussions here. So from there, so already we know that the rate of fall of temperature is directly proportional to temperature. So I'm taking that only. Dt by dt is equivalent to minus K is a constant. The temperature difference is, let us say, theta minus T minus T naught, or we can take in terms of theta. No issue. Okay, in terms of theta, to write d theta by theta minus theta naught equal to minus K into theta. So we will apply both side integration, and the temperature of the body initially when T equivalent to 0, the body temperature is theta 1, and the final temperature is theta after a time t. So integral 1 by x into dx means log x. We are having log base c theta minus theta naught equal to, we are going to have minus kt. Or we know that it can be taken as ln of theta minus theta naught equivalent to minus k. But we have specific limits, so that is theta and theta 1. So now I am writing log base c theta minus theta naught minus log base c theta 1 minus theta naught equal to minus kt. Suppose if you need a graph between the log base c theta minus theta naught and the temperature and the time, so we will have kt plus log base c theta 1 minus theta naught. Suppose if somebody interested in theta minus theta naught graph, so then one second. Now we are taking a graph between log base c theta minus theta naught, that is nothing but ln theta minus theta naught, and time we are taking This is y and this is x and this is c. Y equivalent to minus mx plus c. Y equivalent to mx minus mx plus c. So therefore, you have a straight line with positive intercept and a negative slope. So this graph is very, very important. Ln theta minus theta naught and time. Actually, this is time t graph. This is the time t graph. And one more thing we are going to have. So that is the graph between theta minus theta naught and time. Suppose if you take a graph between theta minus theta naught and the theta minus theta naught and t. So then we will see that from here ln of theta minus theta naught equivalent to minus kt, or log base c theta minus theta naught equivalent to minus kt, or theta minus theta naught equivalent to e power minus kt, e power minus kt. Exponential decay, simply this is exponential decay. So we have exponential decay first, like it will be, this is the exponential decay. Next, we used to think of temperature of sun. We used to determine temperature of sun by using solar constant. By using solar constant. So first we will understand what we mean by solar constant. For example, this is the sun we are taking. This is the sun of radius Kepler, but we have been observing at a distance smaller from the center. So in the three-dimensional way, suppose if you are in the three-dimensional way, if you are imagining. Now at this instant, we are focusing a small part, small unit area at a distance r. Now first we will define solar constant. Solar constant. Solar constant means intensity of radiation. Intensity of radiation. Intensity of radiation reaching. Intensity of radiation reaching the Earth's surface. Simply it is called as, in one word, intensity of radiation. So that is SC, solar constant, generally symbolized by the letter S. S is nothing but intensity. Already we know that intensity means energy by area into area of observation into 2. E means energy emitted by the black body, that is sun. So therefore sigma area 4 pi r square I'm taking into t power 4. But the denominator area is always intensity in the expression intensity, area of observation. But here your area of observation is this 4 pi r square. So this is your area of observation 4 pi r square into 4 pi r square. So energy by time means sigma into 4 pi r square into t power 4. E equivalent to 1 you are taking. And finally, we are having S is equivalent to capital R by small r whole square into sigma into t power 4. So from here easily we will estimate. So at a given place, generally it is having a fixed value of 1.4 watt per meter square. Or by taking the 1.4 watt per meter square, and we know everything capital and smaller. So generally the temperature of the sun is estimated in the order of 5800 Kelvin. So in this way, we will estimate the temperature of